Section 2.2 Polynomial Functions of Higher Degree. Our greatest weakness lies in giving up. The most certain way to succeed is always to try just one more time. Thomas Edison. So today we're going to be talking about polynomials. And these are functions whose degrees are greater than 2. So remember, if the highest exponent for x was a 2, then that was a quadratic function, which is still a polynomial. And then if it was a 1, the highest exponent was a line, which is still a polynomial. But now we're going to look at anything greater than a degree of 3 or more. So the definition, let n be a non-negative integer. A polynomial function is a function that can be written in this form. That's the general form. And each ai, so these numbers in front of the x's, those are called coefficients and are any real numbers. And then the product, so this one and this one and this one, those are called terms. The coefficient of the variable with the highest power is called the leading coefficient. So the one with the highest power is going to be called the leading coefficient, which we'll use quite a bit. And the degree of the polynomial is the highest power of the variable that occurs in a polynomial. Polynomial functions are smooth graphs that only contain rounded curves, no sharp corners. And polynomial functions are continuous. This means that the graph has no breaks and can be drawn without lifting your pencil. So example 1, determine which of the following are polynomial functions. And so one of the important things here in the definition is that n is a non-negative integer. That's the exponent. So if we look at all the exponents here, they're integers. So this is going to be a polynomial function. G of x is equal to negative x times x squared minus 4. And so if I multiply this out, I get negative x cubed minus 4x, and I can see my exponents are non-negative integers. So this is going to be still a polynomial. And then for the third one, we have 5 square root of x plus 2. That square root of x is the same as x to the half power. So anytime you see a root, it's a fraction exponent. And so since half is not an integer, then we say this is not a polynomial. Letter D, we are given a graph. So in the definitions, it says that a polynomial is smooth with no sharp corners and that you can draw it without lifting your pencil. So this parabola is smooth, it doesn't have any sharp corners, and I can draw it without lifting my pencil. So this would be a polynomial. And here there's no sharp corners. These are smooth curves. However, in order to draw this, I would have to actually lift my pencil. When I draw this part, I would have to lift my pencil and draw this part. So that makes this not a polynomial. It's still a function, just not a polynomial. Here, I can draw it without lifting my pencil. There's no sharp corners. So this would be a polynomial. And this one, I can draw without lifting my pencil, but there's a sharp corner here. So that's not a polynomial. Okay. Example 2, identify the degree and leading coefficient. So the degree of the polynomial is the highest exponent in a variable. So this exponent has an x squared. This one has a 3. So the degree is going to be 3, since 3 is the highest of 2, and this one over here. The leading coefficient is the number in front of the term that has the degree, the highest exponent. So this has the highest exponent, so our leading coefficient would be negative 4. The next one, the degree. So we have a 5, a 3, and a 1. So the highest one would be 5. And I'm going to use LC for leading coefficient. And so our leading coefficient would be the coefficient in front of the highest exponent. So that's going to be 5 as well. Here we have a 1 for the p, we have a 3, and so the highest degree would be 3, and the leading coefficient is a -1. Let's look at another example. Okay, so here the highest degree would be 8, and the leading coefficient is going to be 1. So these numbers here, the constants, notice that we don't see the variable x. However, there is an imaginary x here with the coefficient or degree exponent of 0. So x to the 0 is just 1. So this right here is 4 times 1, which is 4. So 4 is the same as x to the 0 power, as 4x to the 0 power. So when you're looking at these exponents, you have 7, 3, 2, 8. The one with the constant, that exponent is 0. Okay, so the degree here is still 8 and the leading coefficient is 1. The next definition is the leading coefficient test. As x moves without bound to the left, x is going to negative infinity, and to the right, it's going to positive infinity. And so the graph will eventually rise or fall. This behavior is referred to as the end behavior of the function. So basically the behavior far left and far right. So we want to know what happens to the graph on the left side and on the right side. Does it fall? Does it rise? So we have steps to determine the end behavior. So the first step is you want to find the degree of the polynomial. Then from this degree, we're going to have two options. Number one, if the degree is odd, then it will have a certain behavior. And number two, if the degree is even, then it's going to have a certain behavior. The second thing that we need is the leading coefficient. And here we have two options too. If the leading coefficient is positive, then something happens with the behavior. If it's negative, then something happens. So we're going to find out what that something is. In order to figure out these behaviors, I want to use 4 functions that we're familiar with. You can try to memorize the definitions, but since we know what these look like, then this will help you determine the behavior of any graph. So we know that f of x equals to x squared is a parabola. The leading coefficient here, or the degree, is 2. And we want to say that this is even, because we're going to use that in a little bit. And then then the leading coefficient is 1, and that leading coefficient is positive. Okay, so let's look at the graph. So the graph for this parabola looks like this. Okay, so the behavior when a function is even and positive, when the degree is even and the leading coefficient is positive, is going to be as follows. If we look at the graph, all the way to the right side, we can see that this graph here is rising. And all the way to the left side, this graph is rising. So we'd say that the graph rises right and rises left. Okay. The next one is f of x equals negative x squared. And so the degree for that is 2, which is still even. And the leading coefficient is negative 1, which is now negative. So the graph, I'm going to call this B. So the graph for negative x squared looks like this. Okay, so when you have a graph with degree even and negative coefficient, then we say that the graph, so to the right it's falling and to the left it's falling. So the graph falls left and falls right. Okay, so in both situations, when the degree was even, the graph does the same to the right and to the left. So it either falls left and right or it rises left and right. Okay, the next one is the x cubed. So the degree here is 3 and the leading coefficient is 1. So the degree is odd and the leading coefficient is positive. So this graph looks like this. It's one of our parent functions. So if we have an odd and positive, an odd degree with a positive leading coefficient, then we say that the graph to the right, you can see that it's rising. Graph rises right. And to the left, we can see the graph is falling. Okay, the last one, f of x is equal to negative x cubed. So the degree here is 3. Leading coefficient is negative 1. So we still have an odd degree with a negative coefficient, leading coefficient. So the graph for this one will look something like this. Okay, so if your degree is odd and you have a negative leading coefficient, then we say that the graph falls right and rises right, rises left. So rises left, falls right. Okay, so again, you can memorize these 4 statements here, or what I like to do is, since we know what these graphs look like, then no matter what problem you have, you can refer back to these graphs to help you get the behavior. So for example, f of x is equal to x to the 4th minus 4x squared. So the 2 things we need is the degree. So the degree is going to be 4 since that's the largest exponent. And the leading coefficient comes from the term with the highest degree or the highest exponent. So this leading coefficient is 1. And so then we ask ourselves, our degree here is even and our leading coefficient is positive. And so you want to think about which graph does this remind you of, or you can look at the statements here. So if we look at these, our degree is even, so that means that this graph and this graph is not going to be in our solution. So it's either going to be this one or this one. And then it's positive, so that means that our behavior is going to act like this one here. So the behavior will have the same behavior as this, which means that the graph rises right and graph rises left. So here I would say that the graph rises left and rises right. Okay. So if I graph that, you can see what it looks like. So we have x to the fourth power minus 4x squared. And so you can see that the graph rises up on the right and rises to the left. Let's look at letter B. So the degree for letter B is 3, and the leading coefficient is 1/4. So my degree is odd. My leading coefficient is positive. Okay. So since it's odd, it's going to be letter C or letter D, and then the leading coefficient is positive. So we're looking at this behavior. So when we graph this, all we know is that the graph is going to rise to the right. So you have something over here, and it falls down. And we don't know exactly what happens in between, which we will figure out in later sections. So for now, we just want to know what the behavior is. So I'm going to say the graph rises right and falls left. And again, it rises right and falls left because the degree is odd and the leading coefficient is positive, so it's going to have this same behavior. The next one, the degree is 6, leading coefficient negative 3.6. So this is even, and this is negative. So we look at our possible graphs here. We're working with these two since their degree is even. And then the leading coefficient is negative, so that means that the behavior will act like this one here. Okay, so we can say that the graph falls right and falls left. Okay, letter D. So here we have to be careful. Notice that all the other problems, these were already multiplied out. But here we have parentheses. So you want to make sure that your polynomial is multiplied out. So negative 3x squared times x is negative 3x cubed. My positive 3x squared. So we're distributing this. And this is times x plus 4. So negative 3x cubed times x is negative 3x to the 4th. Negative 3x cubed times 4 is negative 12x cubed plus 3x squared, 3x cubed plus 12x squared. So let's check again. Negative 3x cubed times x is negative 3x to the 4th. Negative 3 times 4 is negative 12x cubed. 3x squared times x is 3x cubed. 3 times 4 is 12x squared. So my degree here is going to be 4. My leading coefficient, negative 3. You can add these terms. So this is actually 9x cubed. So since my degree is even, and I have a leading coefficient that's negative, then that behavior is going to be an even degree with a negative leading coefficient. So it's going to act like this. So we say the graph falls right and falls left. Okay, let's look at 54. If a polynomial function, if f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros. So remember, we've been talking about zeros in the other sections. These values of x are also called the roots or solutions, or we call them X intercepts. of the polynomial function. The statements listed below are equivalent. If x is equal to a, we say that's a zero of the function f. X of x equals a is a solution. X minus a is a factor, and a comma 0 is an x-intercept. So these all mean the same thing. A polynomial function of the nth degree is a product of n factors, so it would have at most n roots or zeros. The graph of a polynomial function of degree n must have at most n minus 1 turning points. So what this is saying is if your degree is 3, then you should have 3 zeros. Okay. So for example, given the polynomial f of x equals x minus 2, x plus 1, x minus 4, determine the y and x-intercepts. Determine the maximum number of x-intercepts and turning points. So the first thing we want to do is find the x-intercepts, which are the zeros. So to do that, we're going to let y equals 0 and solve for x. So here's my function. And I'm going to let y equal 0. So I said each factor equal to 0, since it's already factored out. And I solve for x. So I'm going to add 2 on both sides. So I get x equals 2. Subtract 1 on both sides. So I get x equals negative 1. And add 4 on both sides. So we get x equals 4. Okay, so these are called our zeros, or x-intercepts. The y-intercepts, or the y-intercept, is we let x equals 0 and solve for y. So if x is 0, we get 0 minus 2, 0 plus 1, 0 minus 4. 0 minus 2 is 2. 0 plus 1 is 1. 0 minus 4 is negative 4. Multiply it out. 2 times 1 is 2 times negative 4 is negative 8. So this is our y-intercept. So notice here that our degree for this polynomial, if I was to multiply x times x, I get x squared, and then x squared times x is going to be x cubed. So my highest degree is going to be 3. And I encourage you to multiply this entire thing out, and you'll see that we still have a degree of 3. And our leading coefficient, well, this is a 1 times a 1 is 1 times a 1 is 1. So our turning points is going to be found by using n minus 1, where n is the degree. So we say degree minus 1. In this case, our degree is 3, so we say 3 minus 1 is 2 turning points. So it's going to have at most 2 turning points. So it could have 1 turning point, anything less than 2, less than or equal to 2. The number of zeros was 3, 1, 2, 3. Notice the degree is 3, so we should have had 3 zeros, which we do. Okay, so let's go ahead and find the behavior, even though it doesn't ask us to. So remember, the behavior is found using this table. So since the degree is odd and you have a positive leading coefficient, so the degree is odd and positive leading coefficient, it's going to behave like letter C. So we say that the graph rises right and falls left. Okay. So we look at the graph, this is the information we have for it so far. We have the zeros, x equals 2, that's right here, x equals -1, and x equals 4. We have a y-intercept of 0, -8, so somewhere down here. We know the behavior, it's going to rise to the right, and it's going to fall to the left. So everything in between, we don't know yet, but we will figure this out in the next sections. Find all the real zeros and determine the maximum number of points. So again, here we have f of x is equal to x cubed minus 12x squared plus 36x. So we can find the zeros first. To find the zero, that's the x-intercept. So we're going to let y equals 0 and solve for x. So here, in order to solve this, we need to try to factor this. So we always check if there's anything in common to all three terms. This has x cubed, x squared, and an x. So I can actually factor out an x. So if I take an x out of here, I'm going to be left with x squared. If I take an x out of here, I'm left with 1x. And if I take this x out, if I factor it out, I'm left with 36. So if we multiply x times x squared, x times -12x, x times 36 is going to be this polynomial. After that, you can see that in the parentheses right here, this is quadratic, so you have two options to solve this. Number one, you can see if it factors, or you can use the quadratic formula if you prefer to use the quadratic formula. I always like to try and factor, and if it's not factorable, then I go ahead and use the quadratic formula. So 36, I need two numbers that when I multiply them will give me 12. So that's going to be 6 times 6 is 36. If I add 6 and 6, I get 12. I need this to be a negative, and this is a positive, so the signs will be the same. So -6 times -6 is positive 36. -6 plus -6 is -12. So now I can set the factors equal to 0. And so here we get x is equal to 6 and x is equal to 6. So I have 3 zeros. Notice my degree was 3. That means I should have 3 zeros, which I do. Although these are the same, we still count them individually. And let's go ahead and look at the behavior. This is the end behavior. So my degree is 3, which is odd. My leading coefficient is 1, which is positive. So my behavior is going to be that the graph rises right and falls left. Okay, so again, for this problem, if I was to graph it, the information I have right now is that at x equals 6, we have a 0. And at x equals 0, we have a 0. And if we were to find the y-intercept, it would be at 0, 0 as well. So we know that the graph is going to rise to the right and it's going to fall to the left. So in later sections, we'll figure out what goes in between. Let's go to the next page. Determine the solutions of x to the fourth minus 4x squared. Determine the maximum number of zeros and turning points. The number of turning points for this one was the degree minus 1, so the degree is 3. So we have 2 turning points. At most 2 turning points. Example 6, determine the solutions of f of x equals x to the fourth minus 4x squared and determine the maximum number of zeros. So whenever they ask for solutions, that still means the same as zeros and x-intercepts, so we're letting y equal 0 and solve for x. So here's my function. So we get 0 is equal to x to the 4th minus 4x squared. I can factor out an x squared. So if I get an x squared out of here, I get x squared minus 4. Try to factor this parentheses. This is perfect squares, so I'm going to have x minus 2 and x plus 2. So this x squared can be the same as x times x. And I go ahead and write it this way so that we don't forget that there's actually 2 here. So now I can say 0 is equal to x, 0 is equal to x, 0 is equal to x minus 2, and 0 is equal to x plus 2. So my zeros are going to be x equals 2. Subtract the 2 here, x equals negative 2, x equals 0, and x equals 0. So you want to be careful here, because at this step right here, if you had said 0 is equal to x squared, 0 is equal to x minus 2, and 0 is equal to x plus 2, then to solve for x here, we take the square root. So we get x is equal to 0, x is equal to 2, and x is equal to negative 2. So here we're only listing it once, but in reality there's two zeros at x equals 0. And so if you take the square root, just remember that there's actually two answers here. You get the plus and the minus answer. The turning points, the degree is 4 minus 1, so we have at most 3 turning points. Okay. So for extra credit, I'm put a star here. For quiz 3, find the end behavior for this example. And this is just for 1 point.